It's the last day of the course today, and we still have one very important topic to cover, and these are photocatalysts. I'm gonna share the screen now with you. Okay. Now, so far we have covered quite a lot of different functional materials. We covered all kinds of functional properties. Then we were talking about the metals, semiconductors. We were talking about polar dielectrics like pyroelectrics, electrocalorics, relaxors, magnetic materials. You heard my colleague yesterday. And now we're gonna be discussing the photocatalysis and the photocatalysts. Well, all these materials, we put a lot of hopes in these materials for future sustainable technologies for environmental remediation or for hydrogen production by water splitting, for instance, and or for the photocatalytic synthesis of different kind of organic molecules. Now, first of all, what photocatalysis is. As the name says, it's catalysis which is assisted by light, by photons. So we will certainly talk about the interaction of light with matter, especially interaction of light with semiconductors. So for that reason, I think it is quite useful if we repeat a little bit about the electronic structure of semiconductors. We will define Fermi level and Brillouin zones, and we will talk about two different band gap structures. Then we will see how the semiconductor interacts with light. We have heard something about that during our lecture on optical properties, but we will extend this knowledge now. Then something about charge transport within the photocatalysts. And at the end, of course, we will see how actually this photocatalytically enhanced reaction take place on the interfaces of the semiconductor with liquid. So this is our already well-known picture showing the formation of molecular orbitals in quite a simplified way. In reality, our molecules are three-dimensional. Well, even if we consider sometimes two-dimensional, but you know, it's everything is three-dimensional in our universe. So we talked in a simplified manner how the valence band and conduction bands are formed. And we know now that the valence bands, they contribute to stability of the system, and so they are bonding, while the conduction bands are anti-bonding. They actually destabilize the system. Now here I just want to show you that in reality, these orbitals, these bands, are much more complex as we have represented them during our lecture. Now here we have a structure of the bands in fullerene, and you can see they're much more complex. Doesn't matter really, we don't need so much to think about this complexity, but we can stay with the principal concepts that we have already discussed. Now I would like to tell you in relatively simple manner what Fermi level is. The Fermi level is something artificial. We have defined it just to help us understand all the electronic properties of the semiconductor under different circumstances. So let's say we have a Fermi level with energy me here. And now, if there is one particular state which has got the energy equal to the Fermi level energy, then the probability for the electron to occupy this state will be 1/2, or let's say 50%. So this comes out of this Fermi-Dirac distribution equation. If we assume that these two energies, epsilon and me, are equal, we would get probability for occupancy of this state to be 1/2. So I will from now on use this particular scheme here. As you say, 100% probability is orange, fully orange, well then it is losing the color when we go up to the 0 probability. Now let's see how that looks in one perfect, let's say almost perfect isolator with very wide band gap, so-called wide band gap semiconductor. Now in this case, we take something higher than 4 electron volts. So the picture should look like that, of course, and the Fermi level in this case will be straight in the middle of the band gap. However, of course, this picture is not correct because we said that these are forbidden energies for the electrons. So none of the electron could have an energy in the band gap. So in reality, in such a material, the situation rather like that. So we do have fully occupied valence band, empty conductive band, and the Fermi level is in the middle. However, there can be no occupancy because we have forbidden energies in this gap. So this is how we define the Fermi level in insulators. Now we can talk about narrowband semiconductors now. Now the situation in narrowband semiconductors should be as it is shown here. Again, we have Fermi level straight in the middle of the band gap. Well, I'm talking here, of course, about pure intrinsic semiconductor, more like a concept. And of course, now the occupancy would increase from somewhere from the valence band gap into the conductor band, from valence band to conductor band. Now, again, of course, we have to forget this occupancy in the band gap because it can be known. So we erase this. But as you see, now we have a different situation. We still have some probability for the electrons to occupy conductive band, and we have some probability that electron holes will be present in the valence band. So these electrons and electron holes then can conduct electricity. So in other words, we have already been discussing this. And we already mentioned Boltzmann distribution, which gives you a number of excited electrons at some particular temperature. So this is something that we have already been through. And we already then, from the number of the charge carriers, we have already defined conductivity of such a semiconductor. So the conductivity is equal to the number of species charge carriers and multiply by the sum of their mobility. Okay, so also then we have seen that the extent of band gap strongly correlates, reversely really correlates with conductivity. Bigger band gap, lower conductivity. And we can easily understand this from the upper picture. More we extend the band gap, less charge carriers we will have present, free charge carriers. Okay, but what is important also is to understand in the term of Fermi level, to understand extrinsic semiconductors. So either how the defects as an extrinsic an extrinsic defect, how they influence the electronic occupancy of the states, or how deliberately introduced dopants do. So here is the picture we already know now. It's a wide band, relatively wide band semiconductor with a Fermi level straight in the middle of the band gap. And now we dope this system with some donor. So there would be the upper limit of the donor's valence band would be close but to the conductive band, but not in it, but in the middle of, but within the band gap really, but close to the bottom of conductive band. So in that case, you see the calculated probability would look like that, but as we know, we can't have any states here. So we will have increasing number of states inside conductive band due to this donor valence band being close to the conductive band. And for that reason, here we got predominantly electrons conducting. So we can call such a kind of doping n-type doping and such kind of semiconductor n-type semiconductor. Quite opposite, if we dope semiconductor with electron acceptor, then we would have the bottom of conductive band near to the top of the valence band. And now if we calculate the Fermi distribution, Fermi-derived distribution, we would come to a picture that I'm showing you here. And the Fermi level just in between of the acceptor conductive band and the matrix valence band. So here, of course, then we see that we have now deficiency of electrons in the valence band, which means actually we have electron holes, and these holes positively charged can conduct electricity, so we have produced a p-type semiconductor. Okay, as I already showed you before, in the 3D crystals, the situation is much more complex in reality. So we have all possible crystal directions, different atoms, different orbitals, and all that we have to consider. So we, of course, then find ourselves some tools to better imagine the complex situations. So in this case, we construct something called Brillouin zones. And these Brillouin zones represent three-dimensional boundaries of which actually is our construction in the reciprocal space. Now, to say with other words, Brillouin zones are unit cells in reciprocal space. As we have in reality space, our unit cells, crystallographic unit cells in reciprocal space, we have Brillouin zones, and boundaries represent kind of unit cell in the reciprocal space. Well, physically, we can consider them as the boundaries, as a break planes on which the constructive interference of the waves would happen. Basically, this is crystallographic concept. Now, on the right-hand side, I'm showing you now the band structure of titania, of rutile titania, along some symmetry directions of the brilliant zones. Now, you see all these wiggles here. Actually, this is representation of many different orbitals that extend through these symmetry directions. What you can also notice here is that for some energies, there's nothing really allowed here, no orbitals in some energy span. And this actually is the band gap. We were talking about band gap, but band gap is what we see now extended into the two-dimensional space of symmetry directions. And from this plot, for this band structure plot, we can then define the band gap. And if we would look on several materials, we would see two different types of band gap. So we first of all have to look for the minimum energy difference between the top of the valence band and bottom of the conduction band from such a band gap structure as we have seen on the previous slide. Now, in some cases, they will be minimum and maximum will be on the same momentum, so one over another. In some cases, they won't be. It will be shifted. So this is how we distinguish the direct band gap from indirect band gap. Now, physically, what does this mean? So it means that when we will excite electron in the case of the direct band gap, we just need to have interaction of an electron with a photon, and then we excite electron from valence to conduction band. However, in the case of indirect band gap, this is not enough. In the case of indirect band gap, we cannot excite electron only with a photon, because this will not change the electron's momentum. So actually, we won't be able really to reach the upper orbital. Now, what we have to do in the case of indirect band gap is to have an interaction of three entities: electron, photon, and phonon. Phonon actually is capable of changing electron momentum in the way that it gives or it accepts some of the energy, some of the momentum of the electron. Namely, there is also something called momentum conservation law. So it means that we can't, in a system as a whole, we can't lose or gain momentum. But in the system as a whole, we can transfer momentum from one entity to another entity. So in the case of indirect band gap, we need to involve three species: electron, phonon, and photon. And of course, such transition, for that reason, will be less probable. Let's talk about this a little bit. Now, of course, it will be less probable because the probability for all three entities to interact among themselves is lower. However, also relaxation will be less probable. So lifetime of such excited electron in the indirect band gap system will, by the role it will be longer. Okay, now first of all, let's talk about photo excitation. So we talked a little bit, but I would like just also to slightly repeat that and extend a bit. So we said that the electron can be excited by a photon only if the energy of the photon is higher than the energy of the band gap. We know that. Now, what we have available here, and what we want to work, of course, is a solar light. And on the right side, you have a solar energy spectrum. And for instance, let's think that this left side here is titania. Titania has got a band gap of, let's say, about 3 electron volts. Now here we get the solar energy spectrum, and what you see is that the visible light span in the solar spectrum is somewhere from 1.6 maybe to 3.1 or even lower than that. So somewhere in that region, yeah? Now, for the water splitting, we need energy of 1.23 electron volts. So we see that with the visible light energy, we can basically split water. But of course, we need to find a catalyst which is capable to do that, but also capable to absorb light in the visible range. Titania, as the most popular and known photocatalyst, has got, as you see, the band gap, which is much higher than the majority of the visible range of the solar light. So really, for instance, if the titania would have energy band gap of 2 electron volts, at least, then titania can absorb all this orange part of the spectrum. But this is not the case. Titania has got very high band gap and can only absorb this part of the spectrum, which majority is ultraviolet and basically no visible light. So this is now an important issue in the photocatalysis, to find efficient semiconductor, which would be capable to absorb majority of the light that comes from sun to our planet. Now, for now, titania is here, but we mainly it's activated with ultraviolet light. Fine, we do have some ultraviolet light in our solar spectrum, but as you see, very little in the term of intensity of the light. So we are losing with titania a significant part of the solar spectrum. Now, of course, we can find also materials with narrow band gap. But it turns out the majority of such materials are not very efficient for a number of different reasons. So this is still intensive, ongoing research development of new photocatalysts or photocatalytic structures or photocatalytic composites that would be able to absorb as much spectrum as possible and still be a very efficient photocatalyst. Okay, now we said the following. So if we have the photon with higher energy than the band gap of the material, we excite the electrons to some upper states in conduction band, and then we coming down by thermalization, heat. But this we consider as the energy loss. And only then we got these active species. So really, when we were talking about the optical properties, we said these electrons will then relax down and emit photon. But in the case of photocatalyst, we don't want that. We want these electrons to stay there for as long as possible and actually cause the photocatalytic reaction. These electrons are active species for the reaction. And of course, holes down there. So we don't want to recombine them, we want to keep them there. So now in terms of that, we also see some benefits of indirect semiconductors. Now, as we said before, the excitation process is much more complex than in the case of direct semiconductor. And consequently, also relaxation process is much more complex and less probable. So we have some chances to keep this electron excited for a longer time. But how we would know if the one particular semiconductor is indirect or direct? So two men very early in the previous century have developed a method which is still today used for that purpose. So they notice that absorption of indirect and direct semiconductors is fundamentally different. Well, we know now why it's different, because it's different mechanism that is required for one or another excitation. Now, what is the process to determine the type of the band gap? So first of all, we measured UV's absorption of the system, and when we have it, we apply to the measurements. We apply so-called Kugelmann equation. This is the equation here with an exponent n here, and you see n here, and then we extrapolate the absorption slope of the semiconductor with this equation using n 1/2 of using n equal to 2. One extrapolation will fit the measurement data. So from that we can distinguish whether the band gap is indirect or direct. If we apply wrong exponent, we won't be able to fit. Now, in addition to that, when we extrapolate down to the value 0, we can also read out band gap value, the band gap energy. So you see in this example here, this is material. I don't know exactly which one, but it doesn't matter. It's one model material for us. This is a material which is indirect semiconductor because we used exponent n is equal to 2, and the energy of the band gap is 2.6 electron volts. Now let's talk a little bit more about the relaxation of the exciton. Exciton we call the pair, the electron hole and the excited electron, we call exciton. So relaxation of excitons can be, of course, on different time scale, and we have already touched this when we talk about direct and indirect band gap. I said indirect band gap relaxations are much slower. Fine. Now a little bit of terminology. So luminescence is the expression for light emission, any light emission, after related to the relaxation. So it means after some energy was deposited in the material, so what was absorbed in the material. So it's a more general expression. But then we have photoluminescence, and this describes light emission, which is stimulated by exposing the material to light. So luminescence we can also call when the electrons are excited by other stimulus, like electron beam, for instance, or temperature. But photoluminescence then narrows down this expression just to light emission stimulation. Sometimes we call it fluorescence, from the term of mechanism. photoluminescence, well, is fluorescence the same, and phosphorescence is also the same. The difference is just in the lifetime of the exciton. So fluorescence, we call material to be a fluorescent material if the emission happens less than about 1 microsecond after excitation. So in other words, the lifetime of the exciton is below 1 microsecond. While phosphorescence takes much longer time. It can be up to hours or days. And by the rule, these phosphorescence emitters are indirect semiconductor. So all this we can also experimentally measure. Now you see this measurements on the right hand side is actually a measurement of the photons as a time resolved measurement. So it means that we were counting at how many photons are emitted at some certain time after the excitation. So you see they start emitting, they reach the peak at 6 nanoseconds after excitation, and then slowly decay down again. So here, from such measurements, we basically calculate the lifetime of the exciton. The lifetime of the exciton is really a time in which half of them decay. Okay, now that's fine, and we said that we want to keep this exciton present as long as possible. And we were talking now more or less about the, well, ideal systems. But we already said that there's no ideal system. So we have to also consider some defects in the crystals. So the defects will certainly reduce well, not in all cases. Some cases they can also increase the lifetime of the exciton, but majority they will reduce the efficiency of the excitation process, or let's say better efficiency of the overall photocatalytic process. Now they can cause non-radiative recombination. Some defect centers are known for that. They can trap the electrons there and slowly cause the loss of their energy and conversion of this energy into heat. So this is what we call non-radiative recombination, because no electromagnetic radiation is emitted. The defects can also absorb the difference in momentum between the carriers. And that is important, of course, for indirect semiconductors. And that will also cause some changes in the lifetime and in the probability for the exciton to relax. In such cases, the energy is exchanged in the form of lattice vibrations. We know in the phonons are lattice vibrations. So they can really accept some thermal energy in the material and increase their phonon energy. So we can talk here about two different materials that behave very differently. I already mentioned one very popular photocatalytic material is titanium, and another is zinc oxide. So in titanium, we will have more radiative than more non-radiative than radiative recombination. while in zinc oxide, the photoluminescence is the dominant relaxation process. And photoluminescence, of course, is radiative recombination because it is luminescence, so it emits some light. Now, we have now some means, some approaches to increase the lifetime, or let's say to suppress recombination, and therefore keep these useful electrons, these high energy electrons available for chemical reaction. So as I said, that all the defects in the structure are mainly harmful. So of course we have to consider the processing way, which would give us as good crystallinity as possible. So we want to enhance crystallinity. Now I'm showing you here the case of the bulk zinc oxide. The bulk zinc oxide, the band gap, well, the band gap is pretty high. However, this does not reflect how zinc oxide reacts with light, because there is a lot of structural, intrinsic structural defects inside the zinc oxide. And these defects give either an N-type doping or P-type doping. So you see different defects as they are shown here. They create different states in the band gap of ideal zinc oxide lattice. In particular, intrinsic zinc, interstitial zinc, so zinc residing on some interstitial site, produces one donor level, which is very close to conduction band. And we have seen in the previous pictures how that influences Fermi level and how that influences the density of electrons in conduction band. So particularly this defect is responsible for N-type conductivity in zinc oxide. And that certainly then, influences all kinds of photocatalytic processes. We can also imagine immediately that relaxation, that the electrons here in the conduction band will have another mechanism of relaxation. They'll be able to drop down to the donor level. So therefore, the defect will certainly negatively influence the lifetime of excitons. Another way is to use electron scavengers. Now, what electron scavengers are? Actually, these are some third species in the system which immediately kind of accept the excited electron, or they can also accept the electron hole and keep it with them. So actually we get some kind of charge separation, and that then disable the other relaxation mechanisms. Now, we have to understand that light absorption doesn't happen just on the surface. Majority happens somewhere in between, inside the photocatalyst. And when then this excitation happens inside the photocatalyst, this electron must come to the surface, otherwise we can't use it for the chemical reaction with surrounding liquid. And therefore, we have to talk about diffusion of electrons. Now, charge transport from site of excitation towards the surface. So in this case, some other processes can happen. This illustration here shows that, we lost the electron. It didn't reach the surface. So what happened? Actually, there are also some traps and some recombination sites in the material where this already dissociated electron during his diffusion towards surface can recombine. So the carriers have got some diffusion length, and this diffusion length should, if we want, of course, to use them usefully as the active species for chemical reaction, this diffusion length must be longer than the size of the particles if we want to optimize the efficiency of this processing. So we have to get this electron as well as electron holes onto the surface of these particles. If the particles, of course, are very, very big, this won't happen because the electrons on the way to the surface will recombine. So that's another thing which we have to consider. And therefore, when we talk about the photocatalyst, in majority or in all cases, we talk about the nanoscience, nanoparticles, the synthesis of all kinds of nanostructures, because we want to reduce the size of particles in order to be smaller than the carrier diffusion length. Of course, carrier diffusion length depends on all this actually. The depends on the diffusivity of the electron, so how fast it can travel, and on its lifetime. How long does it take, to be recombined? So this particular issue, I just give you an example. Iron oxide, hematite, would be really good photocatalytic material. We know it's reddish, a little bit red to brown. Yeah. So it means it absorbs in visible range. So it absorbs much more light than titanium. But the problem is that the recombination inside hematite is very intensive. And the diffusion, carrier diffusion length inside hematite is very, very short. So the solution here would be really to produce hematite particles that would have very small dimensions. So we're talking here about a couple of maybe 10, maybe 20 nanometer in dimensions. Such particles, such small particles that despite very high probability for the recombination, the carrier diffusion length would still be longer than the particle size. Okay. I also want to touch another issue, and this is effective mass of electrons. Actually, the effective mass of electron is related to diffusivity as well. Of course, the electrons, they all have the same mass. The number is written here, small mass, but still, yeah. However, in a solid, this electron is kind of influenced by the crystal field within the electron is moving. All the surrounding atoms, ions, the surrounding crystal lattice has got some field. It provides some field. And electrons, as a negatively charged particles, they feel this field. And of course, they don't move completely freely through the lattice, but they all the time feel the crystal field of the lattice. So the effective mass of electron is just a number which actually represents the influence of this crystal field on the mass of on the electron itself. We call it's a kind of our construction, this effective mass, but we constructed it because we better than can understand the transport properties of the electrons, but also electron holes, charges. transport properties of the charges through the crystal. But it happens that we can also from the band gap structure, we can also understand what material would have lower effective mass of electrons and what material would have higher effective mass of electrons. Namely, it is reverse of the band curvature, which means more bands are curved, lower is effective mass of electrons. Flatter bands have larger effective mass of electrons. So we can even calculate that really from the curvature of the band structure, from the curvature of the band structure around the conduction band minimum or the valence band maximum. So here we go. 2 examples. Titania has got very curvy states. And therefore, it has excellent effective charge transport properties. While hematite, we talk about that, you see how flat these orbitals are. So the hematite exhibit very poor charge transport properties. So extremely small hole diffusion length is the major reason for the pure overall conversion efficiency. And why this happens is because I said, because there's a lot of possibility for holes. In fact, the hematite, actually the major charge carry are electron holes. There are very many possibilities inside the crystal where the relaxation or recombination can happen. Okay, now what I will want to stop now and give you a chance to ask some questions if you have them. And then after the break, we will continue with discussing the surface characteristics. We now more or less discussing the absorption of light and diffusion of electrons towards the surface. But then we have also to discuss surface characteristics. This we will do after the break. And we will also touch a little bit one example of photocatalytic materials. So I'm going to stop sharing now and give you a chance to ask questions.
Yeah, thank you, Professor Valen, for such a nice talk on this photocatalytic materials. So here we have one question from Sumit Kumar. He is asking, while using light source in photocatalysis, light intensity can be calculated, but what is the wavelength of my light source? How to calculate it?
The wavelength of the light source.
Yes, yes.
But the wavelength of the light source, I mean, different light sources has got different wavelengths. We can't, I mean, we need to know how the light is constructed. Could be mercury light, it could be tungsten light, could be some LED diodes. So we don't calculate that. We know we need to know what kind of mechanism is creating light in a source. But if we have some unknown light source, what we do, we actually measure this. We have detectors that can measure the light spectrum, and this is what we normally do. Otherwise, the light, we can know about the wavelength of the light if we, of course, know what is the light source. Because in classical emitters like tungsten or mercury, the light comes out from the band. The wavelength depends on the either atomic emission. of the source, or because of the heat and black body radiation. So there are two principles. In LED diodes, we just should know if what kind of LED diode do we use. Okay.
Yeah, I hope. Thank you, Professor. I hope Sumit is quite satisfied with the answer. And I have one doubt that we are where is this photocatalysis is maximum people are using for this hydrogen production or dye degradation like water purification. So is there as there is any other applications where we can use this photocatalysis?
Well, application of photocatalysis. The most mature, of course, is water purification. Then we use them as a self-cleaning coatings. This is very interesting, and it's quite often already used in practice. Self-cleaning coatings. So we produce a nano suspension of, let's say, titania, very, very small particles of titania, which actually, because of their size, are invisible really for naked eye. And then we coat the window glass with that. What happens is that this titanium on the window glass, if some dirt would be coming on the glass, some organic dirt, when this glass is under the sunlight, the titanium would catalyze decomposition of the organic dirt, and next rain will wash it away. So the windows would stay clean for very, very long time. And in addition, something we didn't talk about, such a coating would also make the window surface to be super hydrophobic. That means that the wetting angle will be very high and water will not spread on the window surface, but will just flow down. So this is one very interesting and useful application. And that's
Yeah,
maybe I
thank you,
should also
Professor.
mention some others. We are talking about water purification and hydrogen production because it's kind of hype. But the photocatalyst can also be used for the synthesis of very different chemical molecules, small chemical molecules, uh, which is yet another field of research. Yes.
Okay, so here I have seen that Mr. Puraram has raised his hand, or he is. So I am unmuting. Hello?
Yes.
Yeah. Is my voice audible?
Yeah, Puraram. Yeah. How are you?
Yeah, wonderful talk. Thanks, Professor Valan. Uh, my question is related to for which type of band gap material is useful for photocatalysis, either direct band gap or indirect band.
Yeah, you see, that is difficult to answer because this particular feature, direct or indirect band gap, is just one of many, many properties that influence efficiency. We talked today about absorption, then about the diffusion, about traps in the crystal lattice, about the carrier lifetimes, and now we will see also surface properties. The development of efficient photocatalyst is very, very complex because there are so many features, so many processes that influence efficiency. In general, if I forget this complexity, I would say, the direct semiconductors, they have an advantage. They absorb more efficiently, but they have disadvantage. They have shorter carrier lifetime, while indirect are quite opposite. They absorb less because the probability for three entity event is lower, but they have higher lifetimes. So, also I would say I can't say in general what would be better because we have to consider too many parameters.
Yeah, thanks. One more cascade question. Uh, can we increase the temperature of indirect material and we can enhance the absorption of the incident photon? Because as increase the temperature, phonon contribution I will increase in that respect.
Yes, that's quite interesting, and I believe there is lack of research in this because I think this is a good idea, and it has been already tested. Yes, it has been already tested. Of course, we can't increase temperature much because normally we are doing these photocatalytic reactions in water media. So yeah, we are limited with. We don't want to boil the water, of course. In addition. Of course, the increase in temperature would increase the absorption capabilities, but unfortunately also recombination. It will reduce the diffusivity of the electrons. But so I think it is again one thing which we have to empirically determine for each material individually and see in what kind of materials the increase in temperature will beneficially influence efficiency as a whole. All kinds of processes that are happening, whether there will be some increase in efficiency. But I think that should again be empirically determined. For each particular process, we can kind of have an idea how the temperature will influence it. But as a whole, what will prevail, whether drawbacks or benefits, I think it's individually case by case for different materials.
Thank you so much, Professor.
Yeah, Professor, I have one question, one doubt regarding this band gap of material suitable for photocatalytic reaction. So, as we know, titanium band gap is 3.2 electron volts. So, its absorption is very much lies in the UV region. So,
Yes.
the, if we want to work in the complete solar range, like from UV to visible, if I want to work with this complete range, so what will be the suitable band gap for working in this range for
Yes.
photocatalytic activity?
Yes. I can answer this. So as I said, theoretical minimum band gap or electron energy for the water splitting is 1.23 electron volts. But we can't split water with this particular energy because of all kinds of different energy losses in the process. So we need electrons with some excitons with some higher energy than that. And estimation is that we need something about 1.9 electron volts up to 2 electron volts to have enough energy despite the losses to split water. But still, that is very fine. That is very good because this is still very deep in the visible range. So normally we are aiming to these band gaps, 1.9 to 2 electron volts. We can reduce absorption of the titanium with some doping. However, for some reason, doping of titanium is not easy. It doesn't want to accept a lot of dopants. So for that reason, we have a very limited possibility here. Ideally, it would be if we can dope titanium with some other elements, and by that doping, decrease the band gap down to 2. But so far, there was not so much success with that. So we are aiming for some other materials. One such material is bismuth vanadate, and there are also bismuth titanate pyrochlores, kind of especially bismuth compounds shows to be promising for the visible light absorption and efficient photocatalysis.
Okay. Thank you, Professor. I get my answer. Actually, I have dogged the barium titrate with different element, iron and manganese. So I am getting the reduced band gap, and with those
Sure.
material, I would like to proceed in this
Yeah.
photocatalytic activity. Thank you so much, Professor. So now it's time to have 30-minute break. After that, we have one more session according to schedule. So
Okay. See you in half an hour.
yes.
Good morning, Professor Valan.
Yes, yes.
Yeah,
Are we ready to
so
start?
yeah, we can start. This one is the last lecture.
Yes.
Yes, yeah, please.
Okay. Okay, hello again for our last hour of this course. Now, what we said is that now we have absorbed the light in the semiconductor. We excited the electrons. Then we diffuse the electrons through the crystals onto the surface of the particle. And now we have to talk about what now is happening on the surface. Okay, now I'm showing you this scheme here. I will explain. Let's start with the scheme A. We have on the left-hand side, we have a typical semiconductor, donor dope semiconductor. We see the valence band level, we see the conductor band level, and the Fermi level. On the vertical line is interface with the liquid that surrounds the particle. The liquid has got some chemical potential, and you see the line, the chemical that corresponds to the chemical potential. So this is situation when immediately after we uh, uh, immerse the particle into the liquid. So before any equilibrium is established between the liquid states and semiconductor states. So now we see that the Fermi level of the semiconductor is higher than the chemical potential of the liquid. At such conditions, it will be possible to the electrons to travel through the interface to the solution. So what will that cause? Now we are moving to the scheme B. It will cause a depletion of the electrons near the surface of the semiconductor. And this depletion will then cause the electron Fermi to equalize with the chemical potential energy. And because electron Fermi energy to equalize with the chemical potential, and because the Fermi level will, as you see, move down so much, it will also together bend the valence band and the conductor band. So we will get something called band bending. And this is very typical for any kind of surfaces, interfaces. So now this band, this situation at the interface, then provides some very different conducting properties to the interface. So actually, it represents Schottky barrier. The electrons can flow in one direction through, but not in the other direction. Now we also have to understand how this barrier now changes under illumination. Now, under illumination, of course, we got then holes and electrons, and the illumination changes the internal fields and separates these two species. So we can get efficiently, you see, we can get one Fermi level for electrons and one Fermi level for holes. So that means that the band bending to some extent can also, if we can use this in practice, then this process of Fermi level separation, we can obtain the charge separation. And why the charge separation would be useful? it would be useful because then we reduce significantly recombination of the on the surface. Namely, imagine the situation when both electron hole and the electron diffuses to surface and meet each other there. Well, they can also recombine on the surface, and we will lose the active species. So also charge separation on the surface is important. Now, all this happens because, you see, that was one question, how can surface be charged? I mean, the surface, if the surface is charged, then we have some unneutralized surface in the equilibrium. But this is not really so, because the charged surfaces, they get covered with oppositely charged species from the surrounding. And this is presented here. You see, we have some metal negatively charged surface, and then the species start accumulating on the surface to, after some time, to completely neutralize the charge. So you see, first layer of it's very dense, layer of species is very dense, and we call that inner Helmholtz plane. And then we also have more diffuse layer, and this is called outer Helmholtz plane. And even further on, they call it Guy-Chapman region, but actually that is just the same structure, just more diluted. Now, we will talk a little bit later more about charge separation, but let's look first now. Let's imagine that we have now everything done right, and the electrons arrived on the surface and the holes arrived on the surface. Now, how would then they react with the species in the media? Now we have first to transfer this electron to the molecules. So that happens mainly in the way that molecules are absorbed on the surface, and then this transport of electron goes from the particles to the absorbed molecules. Well, the same with the holes. Well, in case of the holes, of course, the species from adsorbed species from the media, they donate electron into the hole. So by that, we can obtain breaking of the chemical bond between in the molecules, and the reaction can in fact continue. Now, these new species, either they are directly they're a direct product of the photocatalytic reaction, or they can be intermediates. They can further trigger some new reactions. We can only produce, for instance, during this process, radicals, and these radicals, as being very reactive species, will then later react maybe with some impurities in the water. So here you see a number of semiconductor materials and their band gaps and the position of their valence and conductive bands. So you see, we can choose among quite a lot of materials. So there are some specific trends. I wouldn't like to talk about this because it's just orientational and it's not so important really. But what I want to show you with this picture is that for different photocatalytic reactions, we have a choice of very different materials, and if we know the thermodynamics of the reaction, we can choose in an educated way, let's say, so we can choose proper group of materials. Okay, and now let's see more in details, for instance, how we would get a reactive species from the electrons on the surface and holes on the surface. As I said, the electrons need some molecule from the media to be absorbed on the surface, and then it would be able to jump on this molecule and transform it into some reactive species. For instance, in the case if we have some oxygen dissolved in water, the electron would form the photo generated electron would form superoxide anion, O2 minus radical. So you can imagine that this species is very, very reactive. And what will happen? It will deabsorb from the surface, and when it finds any kind of molecule in surrounding, it will jump on it and oxidize it. Now we have here hydroxy ion, and hydroxy ion then can donate this electron to the electron hole and become an hydroxyl radical as well, yet another very reactive species. And if we have, for instance, some organic pollutants, some dyes or something like that in between, these two will very efficiently degrade the organic molecules. But they can also split water, and we can get hydrogen out of water. So there, I wrote down some reaction pathways for this species, and really I don't think we should go into details of that, but you can see that there's a lot of chemical transformations that can be caused by this species, and there are many different different ways to obtain the final products we want. Either this is hydrogen and oxygen for water splitting, or this is just decomposition of some organics, or what we call mineralization of organics. That means we completely destroy them down to carbon dioxide and water molecules. And the final thing which I would like to discuss are co-catalysts. I already said that it's very important for a good efficiency to separate charges on the surface. So here I would like to present to you how that is done with the co-catalyst. Co-catalysts are often metal clusters that we deposit on the semiconductor particles, or any other, not necessarily metal clusters. They can be oxide, they can be chalcogenides. But the important is that the position of their either Fermi level of or chemical potential is suitable for the same spaces for the charge separation that we really want to achieve. So here I give you some examples. When the contact between the semiconductor, in this case metal, is made, electrons can lower their energy by flowing from the semiconductor band into the metal. This is pretty much similar as we have seen before when we discussed the interface of the semiconductor in liquid. Now this process will build up a charge on the metal semiconductor interface, and this charge will deform the band structure. We will get the band bending, as we said. This continues until the chemical potential in the semiconductor reaches equilibrium with the Fermi energy of the metal. So we know that from other picture before. So this is everything very similar as in the case of the liquid medium around. So we get depletion layer where we lack some electrons or electron holes, but more importantly, we get this jump here in the Fermi level. So it means the electron can travel in one direction, but they cannot in other directions. And the holes, quite opposite, travel in opposite direction, but forbidden to travel in the initial direction. So that will make electrons go into the co-catalyst, while holes will not go, or vice versa. And in practice, this means that we will accumulate electrons in the co-catalysts, while in the surrounding of the co-catalyst, there will be excess of holes. So this is what we call charge separation. And this is actually a very efficient way to increase the photocatalytic efficiency. Okay, so this is now a picture here in the middle, upper picture in the middle is where this process is illustrated. You see electrons are going into the co-catalyst while the holes are not allowed to go there, but they really go on to the surface around the co-catalyst. And then we can have these processes that we discussed before separated in space. So if we want N-type semiconductor as shown here, they're mainly metals, but also some combination of metals and chromium oxide, for instance. While for the P-type semiconductor, where the process with holes and electrons would be just opposite. So they're like very known iridium oxide with titanium oxide, but also manganese oxide. Okay, so here we're gonna stop talking about the fundamentals of photocatalysis. What I want to do for the end, I would like to illustrate you that not only, I mean, it's very important, of course, to understand all these processes that are happening in the photocatalytic reaction, or let's say they're happening before we have some efficient photocatalytic process going on. But we can influence these things also with some clever material engineering. That is very interesting, creative way to increase the efficiency of the material, despite maybe some drawbacks of that the material can exhibit. So just one example, just to know that we have a lot of different mechanisms really to increase the efficiency of materials that we are developing. So this is zinc oxide. In this case, it has been investigated as a potential material for solar cells. But as we heard before, it is pretty much the same issue. So the solar cells, we just collect the electrons that are coming up to the surface and run them through some circuitry. While in the case of the photocatalyst, we use these electrons for chemical reaction, but the processes are same, so I can really demonstrate what I want to demonstrate to you on this particular case. So zinc oxide has got some issues. We talk about that, a lot of defect structure and so on. So it's difficult to really to work on the crystal lattice itself and improve it so much that we would eliminate defects and increase the efficiency. But we can create some other approaches in order to increase the efficiency. Namely, despite we were talking about the absorption of light in the crystals, But if you remember optical properties, no absorption is perfect. There's always some reflection from the surface, even in semiconductor and so on. So if that reflection is significantly, we are losing this light and we are not using it for our purpose. So for that reason, we can be smart and say, well, okay, but let's create structures, nanostructures, that will capture this light in a kind of maze and won't let out even a reflected light. And even when we get a recombination, the photons are emitted. This can also then reabsorb even these emitted photons. So that was an idea behind the story I will tell you now. So I can wait, I got a technical problem. Okay, so this is the idea. You see, when light comes in, we capture it, and we don't allow it to go out until it is fully absorbed by the material. So, well, it's easy to say, but a little bit more difficult to provide such a system. Now we have to have enough wide band gaps in between of the particles that light would go inside. So somewhere about 7 nanometers, you know, this is the wavelength of the visible light limits. And of course, it is also good if we introduce all these features that help us to separate charges later, so also to cover these areas with quantum dots. So this was an idea. So how can be done? Of course, it has to be done individually for each system. But for zinc oxide, there is a method. So we electrochemically, we can deposit a particular mineral on the electrodes. And if we do this electrochemical process, you see, we will grow on the electron a maze of such crystals of this composition. So this is the crystal structure. It contains zinc and also other kind of ions, hydroxy, chloride, and some water molecules, like it's shown here. So we have layers of zinc, in fact, layers of zincs, and in between all these different little ions. But then, this is thermally not stable system. We heat it up and we start decomposing it. And this system decomposes its zinc oxide and it creates a lot of pores inside, increasing surface energy. And of course, the pores are created because we are losing so much material out of this crystal. But we maintain the shape of original crystals and we maintain this maze of hexagons. In addition, then when we do this, we also create co-catalysts. In our case, cadmium sulfide and cadmium selenide are two examples. And very easy by just dipping the samples into cadmium and cadmium solution, and then in the case of sulfide and selenide into their solution, and rinsing and repeating this many times, and eventually this co-catalyst in the form of a small clusters will deposit on the zinc oxide. So on the left hand side, you see like uncoated zinc oxide, and on the left hand side, you see coated with the cadmium selenide. You see it's becoming a little bit rough surface, and this actually is the surface covered with the co-catalysts. And suddenly you see, I will show you, this is absorbance of this system. Pure zinc oxide does not absorb above 400 nanometers, while with all these co-catalysts applied, we increase the absorption in the visible range all up to 700 nanometers. And then we tested the properties, photovoltaic properties, and you can expect already from the absorption curve that it will be much more efficient in the case when the zinc oxide is covered for photocatalyst. So you see it's the red line, it's all the down. Well, then we are with the catalyst, we obtain much better electron production, if we say so. Yeah. In the case of photocatalyst, we can then collect these electrons, while in the case of in the case of photovoltaic cells, we collect these electrons. In the case of photocatalysts, we can use it for the reaction. So this was here just for you to show you, that we also can, if we think a little bit creatively, we can also trick the nature a little bit, and by smart material engineering, we can significantly increase the properties and performance of material. So why I'm telling you, that's just another graph, but it's saying the same, just how much with time we have gained. We have gained in the current. Why I'm telling you this? I'm telling you because I want to challenge you, and I want to induce in you the creative thinking. So it's not all just bare physical properties that we need to understand, but we need to think how to overcome obstacles. There are many ways, and of course it's not easy. If it would be easy, it would already be done. So it is difficult, but this is why we are learning all this material science, which is hard topic, just in order to do difficult things. And difficult things, of course, well, unfortunately, difficult things are there waiting for us to develop new technologies for the future. So with this, I would like to conclude my course. I hope I was pretty much clear enough that you were able to get some new knowledge, some new insight into the topic of functional materials. I hope that I lighted a spark of interest for this particular research and these particular technologies in you. So, and that in some time, your name will be written on the important research papers or on important patents from the field of materials and materials technologies. So with that, I still would give you opportunity for the final questions, which I would happily answer to you.
Thank you, Professor Valent. I would request to all the participants to raise their hand or post their query regarding the last lecture. Professor, I have one question. Like in the last slide, you have shown that Giordano decorated with cadmium sulfide and cadmium selenide nanoparticles
Yes,
that increase the overall performance of this photocatalytic activity of Giordano.
yes,
So, have you compared the work for bare cadmium selenide and cadmium sulfide itself? So, in that case, we can compare the efficiency, whether it is only improved in the case of heterostructure or in bare material, we are getting the good enough efficiency in case of cadmium sulfide and selenite itself.
Well, I didn't really catch exactly what you're asking, but yes, you see, we have seen this significant difference when using cadmium sulfide and cadmium selenide as the co-catalyst. So why this is so? It's difficult to say. Certainly, it is not straightforward to compare cadmium sulfide in a bulk form and cadmium selenide in the bulk form, because as a co-catalyst, they have completely different role. And why this difference occurs is most probably because of the efficiency of the charge separation. This is our guess, but we have no solid proof for that.
Okay, okay, Professor. I have one question from Sumit. He is asking that I have heard for an ideal solar cell band gap of 1.4 to 1.6 electron volts suitable to observe the maximum number of photons from the sun radiation. So copper oxide have band gap around this range. So his question is why you have used ZNO2 solar cell? Any special reason behind it?
So I will just repeat the question if I understood it right, because I have problem hearing because of technical issues. So is the question why we do not use copper oxide in the solar cells?
Yes, yes, yes. It is like this.
Okay. So really, in the solar, I don't know exactly why not copper oxide, but I know that apart from just the ability of the semiconductor, to absorb the light, there are so many other processes that we need to take care of. And in the copper oxide, copper oxide can have very different valence states. So there could be a photocorrosion present, which means that the aging of such a cell would be an issue. For instance, just irradiation can cause the change in the valence state of copper, which then would cause degradation of the photocatalytic properties. Who knows? Maybe like iron oxide. Iron oxide would also be very suitable. However, the recombination in iron oxide is so high. So many different materials which could be useful with respect to their band gap, they are not, because there are other issues with them. Like I said, like aging, photocorrosion, or recombination, or any other issues.
So yes, I hope Sumit you have received your the answer. So I request all the participants to ask their query if they have any doubt regarding the last session or regarding the whole event we have organized. We are at the last final moment of the event. After that, we have an exam. So I'd like to ask myself, oh, we have received one question. Yeah. So Sumit is asking a catalyst which is more suitable for hydrogen production for water splitting. What kind of material which can give us the best result of hydrogen production? Means he
Okay.
is asking.
Historically, the water splitting was observed on the titanium. Still, titanium, I think, is very suitable. However, we know now what is the problem with titanium. It is the problem that it absorbs only a small part of spectrum there, in UV range. So for visible light, a lot of research is going on bismuth vanadate, bismuth vanadium O3. This is material which shows a lot of promises. And then I would also put into that group of visible light, water splitting photocatalysts, different kinds of bismuth titanates, bismuth titanate pyrochlores, for instance. For some reason, bismuth lone electron pair influences the electron structure of the systems, and many times semiconductor containing bismuth would exhibit band gaps that are quite suitable for absorption of visible light. For that reason, such compounds are also colored. And quite some of such bismuth compounds showed potential for the water splitting.
Yeah, thank you, Professor Valant. And any other question from the participants?
Yes, sir. There is one question from Ashok Kumar. He is asking, what is the difference between free exciton and bound exciton in photoluminescence spectrum of titanium oxide?
Can I repeat to see if I understood right? What is the difference between free exciton and bond exciton?
Yes, in photoluminescence spectrum.
Now we have excitons. Excitons are excited species, yeah? So when we initially get excitation in a material, we move electron from valence band to conductor band. So we have there inside this particular ion or atom, we have present electron, an electron hole very close, in very close proximity. So there is a force between them. Electron negatively charged and electron hole positively charged. So there is still a kind of force between them. So we call their bond. So we need to dissociate them first. We need to break this electrostatic bond between these two excitons. And when we do that, we get then free exciton, which can then diffuse towards the surface.
Okay, I hope Ashok you have get the answer. So thank you, Professor Valen. Now, Professor Mahesh, it's over to you.
Yeah, so thank you, Professor Valla, for conducting this excellent lectures, this one tutorial, this one, and thank you all the attendees, this one, for participating in this GYAN course. And I hope you have benefited from this course. You can submit your feedback, this one, and we will this one share the feedback form, so you can give your feedback, because we have to submit this one to GYAN. And I would like to thank this one volunteers, Amit, Nipun, again Ashok, Sumit, Amit. They have beautifully this one organized this one complete GYAN course, this one. So with this one, we will close this one. So thank you all, and special thanks to Professor Valant, this one. Okay, on the holiday also today you have delivered the talk. So thank you very much.
Thank you to you, Professor Kumar. It was my pleasure, although a little bit less pleasure. If I would be there, it would be even better pleasure.
Yes, yes, definitely more interaction this one in the physical mode, but because of the situation, this one,
yes.
yeah, we have done through online, but in the future, through some other scheme, we will invite you this one at IIT Jodhpur, and we will conduct some other program.
Great. I'm looking forward. I would also like to thank attendees, for being patient and listening to me whole week long. And well, if you have any further queries, I'm available to you. So don't hesitate, to send some emails over, I will be happy to reply.
Yeah,
Thank you.
definitely. So participants, they can approach directly if they have any question, this one related to this course. They can write to me or they can write to Professor Valvan, this one. So yeah, so they can write basically. So with this one, I think we will close this session and thank you very much.
Thank you. Thank you. Goodbye to everyone. Goodbye.
Yeah, thank you all. Thank you, Amit and Nipun, for handling this one.
Professor Valant, I would just like to request you to kindly share the slides of lecture 10 and 11 so that we
Yes,
can.
I will do that. I will do that immediately after this
Okay,
session.
okay, because we are preparing questions on it, so it would be better.
Yes, I will do that immediately. Yes.
Overall,
Okay.
thank you, sir. Thank you.
Thank you. Goodbye.
Yeah, thank you. Bye.
Yeah, there is an important announcement for all the participants that we will send a Google form for question exam of this event and the feedback form also. So you are requested to fill the feedback form and this exam within 2 hours. 2 hours is the limiting time. Questions are very limited. You can easily attempt all the questions within the time. So you are requested to be there at 6:30. So you can complete it by 8:30. It will be in online mode. We will share a Google form with each participant. So you are requested to attempt the exam and requested to fill the feedback form also. Thank you so much for attending this Gyan course on functional materials. We will send it, Chintak, we will send the Google form at 6:30 p.m.